Assalamu alaikum. In this video, inshallah, we will start solving about diesel cycle. In this question, we have air, okay, air standard diesel cycle. So we have diesel cycle. Diesel cycle, these are the PV and TS diagrams for diesel cycle. In Otto cycle, after the isentropic compression process, we have the constant volume heat addition process. But in diesel cycle, after the isentropic compression process, we will have constant pressure heat addition process. Okay, the pressure is constant, V2 equal to V3. But in Otto cycle, it was V1 equal to V2 V2 we had V2 equal to V3. Okay, V2 equal to V3. That is the only difference between diesel and Otto cycle. But for the compression ratio, a compression ratio of 16, we have compression ratio of 16. Usually in Otto cycle, the compression ratio was the ratio between V1 over V2, or the V maximum over V minimum. Here also the same. For this cycle, it is the ratio between V1, the volume at BDC, or the maximum volume, over the minimum volume at state 2. Okay, but for Otto cycle, the maximum compression ratio that we can reach for Otto cycle was 12. Okay, but here for diesel cycle, we can reach more than 22 or around 24. Okay, for the compression ratio value. Okay, that is why I draw here the constant volume heat addition process. I didn't go until I reach state 2 and then draw a line upward to V3. Okay, so it will have a compression ratio less than the compression ratio for diesel cycle, that is for Otto cycle. Okay, why we have a compression ratio for diesel cycle is higher than the Otto cycle? The problem that we have in Otto cycle, that there is at the beginning of the compression process, we will take from the intake valve air plus fuel mixture. Okay, so for the gasoline engine that operates under the Otto cycle, we have air plus fuel mixture. Okay, and then this air plus fuel mixture, we have isentropic compression process, and then the spark will initiate the ignition for the air plus fuel mixture, and we will have a heat addition here for our Otto cycle. That is the PV and TS diagram for Otto cycle. Okay, but for diesel cycle, at the beginning, we only have air. Okay, we don't have fuel. Okay, that is the other difference between diesel and Otto cycle. Okay, and you already have air. Okay, and the fuel is then injected using fuel injector. Okay, and the fuel injector is represented in diesel cycle at this line, the constant pressure heat addition. Instead of the fuel injector, we will have QN. Okay, this will cause that we cannot reach a high compression ratio, because at a certain temperature, okay, that is the process from 1 to 2. When we reach here 1 to 2, we cannot go more like this and reach and put state 2 at here at this point for Otto cycle, because at a certain temperature, we call it auto ignition temperature. Okay, auto ignition temperature. At this temperature, the fuel will start to burn without reaching the spark. Yani we will have a burning or initiating for the ignition before reaching the spark. Yani if we have the piston cylinder, okay, if we have the piston cylinder for Otto cycle, okay, we will have ignition. We will have ignition for the fuel plus air mixture. Okay, and then before we reach the spark didn't work yet, and we didn't use the spark to initiate the ignition. Okay, and then when we reach the ignition, when we reach the spark, the heat addition process, the spark will start to burn the fuel and air again. So we will have also an ignition and explosions here. So this explosion from the spark and the explosion because of the auto ignition temperature, because you increase the temperature to very high temperature and the fuel started to burn without using the spark, then you will have a knock. We call it knocking, because this knocking will or this collisions between the explosions here will cause a high noise, and this noise we call it knocking. Okay, and this will increase the pressure and temperature and will affect the wall of the walls of the cylinder. Okay, that's for fuel air. Okay, that is the problem. We cannot increase the constant the compression ratio, because by increasing the compression ratio or reducing the volume to a state like here put you can put here too. Also the pressure is increasing, like here the pressure is higher than this pressure, and also by increasing the volume, okay, and increasing the constant pressure, the compression ratio. The compression ratio means V1 is decreased to V2 here. The temperature is also increased. Here the temperature is higher than the temperature at 2 here. Okay, so the temperature and pressure will increase, and this will cause the knocking. Okay, and then the pressure and temperature will increase and will affect the walls of the cylinder. But for the diesel cycle, we don't have this problem because we don't have fuel at the beginning, so we can compress the volume to be at state 2 here in more than the Otto cycle. Okay, and then after this we will have the fuel injector, and by increasing or putting the fuel will absorb heat from the hot air, okay, and will burn without a spark. That is also another difference in diesel cycle, that for diesel cycle we don't have a spark, but we have fuel injector, and the fuel will absorb heat from the hot air and then will burn by a self-ignition. It doesn't need a spark. Okay, in diesel cycle, in Otto cycle, then we will have, after the constant volume heat addition, we will have isentropic expansion like this. So in Otto cycle we lost work here because the work is the area enclosed under the PV diagram. Okay, so we lost work, this shaded red area, the red shaded area. Okay, we lost work, but we used Otto cycle because sometimes we don't need this huge amount of work, so we use Otto cycle. So that is why the compression ratio for Otto cycle is for diesel cycle is higher than the Otto cycle, and you can read about this in the book. We have the temperature at which the fuel ignites without the help of spark. Okay, we call it the ignition temperature during the combustion process, causing an early rapid burn of the fuel. The fuel will burn early at some point or points ahead of the flame front, without the spark, without a flame, followed by almost instantaneous inflammation of the end gas. This ignition of the fuel, called auto ignition, okay, produces an noise. We have a noise which is called engine knock. Okay, that is for the theory question. What is engine knock, or explain why the compression ratio of diesel cycle is higher than Otto cycle. That is the reason. Okay, that for Otto cycle we have air plus fuel mixture. Okay, but for the diesel we only have air, and then we will inject the fuel. So that is the reason we can have a compression ratio higher than Otto cycle, because the fuel will burn because of the auto ignition temperature. The auto ignition temperature, the fuel will burn with itself, okay, without the need of spark. Okay, returning back to our question. So we have R equal to 16 and a cutoff ratio equal to 2. Cutoff ratio RC. Okay, what is the cutoff ratio? The cutoff ratio is the ratio between the volume V3 over V2. So between this point, the volume at this point V3 and the volume at this point V2. Okay, we call it cutoff ratio because at state 3 we call it also this point cutoff point. At this point we stop injecting the fuel. Okay, that is why it is called cutoff. We stopped injecting the fuel. Okay, this cutoff ratio is RC equal to V3 over V2. And we will have another cutoff ratio in a dual cycle, and it will have another numbers. It will not be 2, 3. There was a question before in the theory question, what is the cutoff ratio for diesel and what is the cutoff ratio for dual cycle, and the states numbers if we started by the compression process at state 1. Okay, so that is for RC. At the beginning of the compression process, that is a new sentence, air is at 95 kilopascal. So at the beginning of the compression process, so at state 1 here, B1 is equal to 95 kilopascal, and T1 is equal to 27 degrees Celsius. Okay, so and this in Kelvin is 300 Kelvin. Accounting for the variation of specific heats, yani variable specific heat. So okay, we have variable specific heat, and we will solve this question after we end with variable specific heat with constant specific heat. Okay, so we can know how to solve this cycle in both assumptions. Okay, determine the temperature after the heat addition process. The heat addition process Qn is Qn here from 2 to 3. This is the heat addition process. So after the heat addition process, he means T3. Okay, the end of the heat addition process. Yani. Okay, so T3. He wants to find T3. Okay, T3. The heat addition process is the process that replaced the fuel injector and replace the fuel will burn because it absorbs the air, the heat from the air. Okay, that's why we have Qn here. For part B, the thermal efficiency. Okay, and for part C, the mean effective pressure. Okay, the thermal efficiency for diesel. Okay, diesel is like this. Okay, so for T3, I want to find T3. How can I find T3? I have this is the equation sheet. T3, I can see it here. Okay, I can't see it in any other equation. I have RC, it is given in the question, but I don't have T2. So I need to find T2. And in order to find T2 is at state 2, of course. Okay, I need property or something at state 2 also. Usually in variable specific heat we deal with relative volume. Okay, in diesel, Otto, and dual cycle. In Brighton I think we will have maybe BR, we'll see. Okay, inshallah. So I need VR2 in order to find T2. The relative volume VR2 is here in this equation. I have R, but still I don't have VR1. Okay, I need VR2 to find T2, and I have R, but I don't have VR1. In order to have VR1, it is at state 1. I need something at state 1. In the question is given to me that T1 is equal to 27 degrees Celsius or 300 Kelvin. So I can use T1 in order to find VR1, and then use this equation R equal to VR1 over VR2, so I can find VR2. Then using VR2 I can find T2. So then using this equation RC is equal to T3 over T2, I can find T3. Okay, so let's draw this process that I have T1, and this T1 will give me VR1. Okay, using table A17. Okay, and then from VR1 I can use the equation for the compression ratio. Okay, so I can find VR2, R equal to VR1 over VR2. And from VR2 I can use table A17. Okay, to find T2 using table A17. Okay, and from T2 I can use this equation RC equal to T3 over T2, so I can find T3, and that is for the first requirement. Okay, what about the thermal efficiency for diesel cycle? Thermal efficiency for diesel cycle, the usual equations. Okay, is W net over Qn, and W net is Qn minus Q out. So I need to find Qn and Q out. Okay, Qn and Q out. For Qn, I need to find H3 and H2. Let's start with the states at the beginning. 1, 2. يعني we start with the first states. So for H2, do I have something or property at state 2? I already get T2 here, okay, from VR2. So I can get also from VR2 H2. Okay, why not why only T2? I can get H2 also from table A17. Okay, table A17. Okay, and what about H3? I already have something at H3. From the part A, I found T3, so I can use T3 to get H3, okay, using table A17. Okay, so by using H3, I can find Qn. Okay, so Qn. Okay, let's write that thermal efficiency for diesel cycle that we want to find. That's for part B. Diesel cycle is equal to W net over Qn, and Qn is equal to H3 minus H2. Also, this is equal to 1 minus Q out over Qn. Okay, but we will find the W net because we need at part 3 mean effective pressure. Mean effective pressure contains in its equation W net, so that's why I want to find W net. I will not use this equation, okay, but you can use this equation. You already will find Q out. Okay, Qn is equal to H3 minus H2, and Q out is equal to U4 minus U1. U4 minus U1. Okay, and W net is Qn minus Q out. So Qn minus Q out. Okay, so now I've found H2 and H3 يعني just by this chart or by this, I don't know what is this. Okay, okay, what about Q out? Here we start with state 1, U1. I have T1 at the beginning, so I can use T1 to find also U1, okay, from table A17. Okay, what about U4? U4, I need a property at state 4, okay, but I didn't find anything at state 4. So usually in this variable specific heat assumption with diesel Otto dual cycles, we use the relative volume when we don't have a property at a state that we want to find other property at this state also. Okay, so I am searching for VR4. Okay, and VR4 is only in this equation. Okay, but to find VR4, I need VR3, R and RC. R and RC are given in the question, but VR3 is not given, but I can find it using that I will find T3 at part A. So why only getting finding H3? I can find also VR3. Okay, so from table A17, and then from table using VR3, okay, I can use this equation, okay, to find VR4. This equation, which is VR4 over VR3 is equal to R over RC. Okay, and then from VR4 I can find U4 using table A17. Okay, and by this I found everything that I want, and for the mean effective pressure, the equation, the usual equation, where is the usual equation? I didn't put it here, okay, but whatever. Oh, okay, it is here. No, it is not here. Okay, for the equation is like this. The mean effective pressure, we saw it in diesel cycle for part C. The mean effective pressure is equal to W net V1 over 1 minus 1 over R. And for V1, I can find it using the ideal gas law. As usual, V1 is equal to R T1 over B1. Okay, R is 0.287. I really didn't put it here. Okay. Okay. This is the equation, the usual or the most used one. Okay, and we find the V1 from the ideal gas law, and R, its value is 0.287 from table A1 or table A2A. Okay, so and now we finish the question. You can move in the video because all what I will do next is just interpolation and doing this. That is why I draw this diagram, that to save time, just go for the solution of constant specific heat assumption. Okay. So I will start solving and doing interpolations, inshallah. We already solved the question, but we have to plot the numbers. Okay, so I will start using what we wrote, that we have T1 300 Kelvin, and we will use it to find VR1 and U1. So at 300 Kelvin, thermodynamics table, 300 Kelvin, we have U1 equal to 214.07, and VR1 is 621.2. So VR1 is 621.2, and it is dimensionless quantity, and U1 is 214.07 kilojoule per kilogram. Okay. Then I will use the compression ratio equation VR1 over VR2. So I can find VR2. VR2 will equal VR1 over R, and VR1 is 621.2 over R, which is 16, and will give me that VR2 is equal to 38.825. I will take this VR2, okay, and make interpolation to find T2 and H2, okay, T2 and H2 using table A17, okay. So I will, this number 38.825. 38.825 is between these two numbers, okay. So I will make interpolation and find the H and find the temperature T2. Okay, so let's make the interpolation. Okay, T H VR 860, T2 880, 888.27, H2 910.56. VR is 39.12, VR2 was 38.825, 36.61. So T2 minus 860 over 880 minus 860 is equal to H2 minus 888.27, 910.56 minus 888.27, and this will equal 38.825 minus 39.12 over 36.61 minus 39.12, and this will give you that T2 is equal to 862.35 Kelvin, and H2 is equal to 890.89 kilojoule per kilogram. RC is equal to T3 over T2, and then T3, that is the first requirement at part A, we already calculate T2 and we can use the cutoff ratio. So T3 is equal to RC times T2. RC is 2 times 862.35, and this will give me 1724.7 Kelvin. I'm just following this diagram or whatever. Okay, we found T3 from here, R3 equal to T3 over T2. Then I want from T3 to find H3 and VR3 using table A17. Okay, so I will search for this temperature in table A17, 1724.7. 1724.7 is 24. Okay, is between these two numbers. Okay, so I will make interpolation in order to find the enthalpy and the relative volume. Okay, so let's do the interpolation. THVR, T is 1700, 1724.7, 1750, H is 1880.1, H3 1941.6, VR is 4.761, VR3 I want to find VR3, and this one is 4.328 from the table A17. So the interpolation will be 1724.7 minus 1700 over 1750 minus 1700, and this will equal H3 minus 1880.1 over 1941.6 minus 1880.1, and this will equal VR3 minus 4.761 over 4.328 minus 4.761, and then VR3 and H3 will equal to 1910.48 kilojoule per kilogram, and VR3 is equal to 4.547. The next step was using VR3 and finding VR4 using this equation. Okay, VR4 over VR3 is equal to R over RC. Okay, so VR4 over VR3 equal to R over RC. And if you don't know why it is equal like this, this equation, VR4 over VR3 is usually equal to V4 over V3. يعني the ratio between the specific volume is equal to the ratio between the relative volume. Okay, V4 and V3, we can divide both of them by V2. If we divide V4 over V2 and then divide V3 over V2 also, okay, we will get R over RC, because R is equal to V4 over V2. Okay, and because V4 equal to V1, that is why I can replace V1 equal to V4. Then V4 over V2 is R, and for RC is V3 over V2. So now I have R over RC. That is why this equation is like this. So but I can say that this one is R and this one is RC, and already this is equal to VR4 over VR3. Okay, that's why or from where this equation came. Okay, so VR4 then will equal to VR3 times the ratio between the compression ratio over the cutoff ratio RC. Okay, so VR4 is equal to 4.547 times 16 over 2, and then VR4 is equal to 36.376. Using VR4, I can find the internal energy, specific internal energy, using table A17. Okay, so I will go to the table for VR4, 36.37, 36.36, 36 is between these two numbers, okay, 0.37. It is near to this one, you can approximate, but to be accurate we will do interpolation, okay, and I will find u. Okay, so u and we are 4, 657.95 over u4, 674.58, and this one is 36.61, 36.376, and 34.31. So u4 minus 657.95 over 674.58 minus 657.95 is equal to 36.376 minus 36.61 over 34.31 minus 36.61. Okay, so finally U4 is equal to 659.64 kilojoule per kilogram. Okay, and now I can find W net. In order to find W net, I have to find Qn. So Qn is equal to H3 minus H2. H3 is 1910.48 minus 890.89. So Qn is equal to 1019.59 kilojoule per kilogram. And Q out is equal to U4 minus U1 and is equal to 659.64 minus 214.07. So Q out is equal to 445.57 kilojoule per kilogram. Then finally we can find W net. W net equal to Qn minus Q out and equal to 1019.59 minus 445.57, and this will give you that W net is equal to 574.02 kilojoule per kilogram. And then for the thermal efficiency, we are doing all of this for thermal efficiency for diesel, okay, is equal to 574.02 W net, okay, over Qn 1019.59, and this will give you 0.563 or 56.3%. For part C, the mean effective pressure is equal to W net over V1 1 minus 1 over R. Okay, for V1 is equal to R T1 over B1. B1 is given in the question also. Okay, R is 0.287 from table A1 or A2A. Okay, times 300 Kelvin over 95 kilopascal. So, and this will give you 0.9063 meter cubed per kilogram. Okay, that is for V1. Then for the mean effective pressure, 574.02 times 0.9063 times 1 minus 1 over R, which is 16. This will give you that the mean effective pressure is equal to 675.59 kilopascal. So we finished the question using the variable specific heat. So what about the constant specific heat? So let's solve the question again, but using constant specific heat. Okay. I want also to find T3 thermal efficiency and the mean effective pressure. Here I can find T3 using which equation? I can use the same equation. I have RC, okay, and then I can use I can find T2 and then calculate T3. Why I cannot use this equation? It also contains T3 because it also have T4. I cannot solve for 3 and I don't have 4. I start from the beginning, from 1, 2, 3, and then going to 4, step by step. I take the first state, then go to other states. Okay, so start with 2, so you can find 3. You cannot use 4 to find 3. That's why I cannot use this equation now. Okay, so how can I find T2? I have already RC given the question. T2 can be found from here. I have T1 given the question. I have R. K is 1.4 from table A1, from table A2A. K is 1.4. Okay. So I can use K equal 1.4. Find T2, then find T3. Okay, that is for T3. So what about the thermal efficiency? Okay, so let's find now T3, then we can go to the thermal efficiency. Okay, so I need to find T2 first. So T2 is equal to T1. Let's change the color, okay, because it is constant specific heat. So T2 over T1 is equal to R power K minus 1. Okay, this equation. I have T1 in the question, so T2 is equal to T1 R power K minus 1. T1 is 300 Kelvin, R is 16 power 1.4 minus 1. Then T2 is equal to 909.43 Kelvin. And then for part A, I want to find T3. T3 is in this equation, RC over T3 over equal T3 over T2. So T3A is equal to T2 RC, and then is equal to 909.43 times 2. Then T3 is equal to 1818.86 Kelvin. Okay, now I found T3. What about the thermal efficiency for diesel? The same equation, I need to find Qn and Qout. But Qn is equal to Cv T3 minus T2 and Cv T4 minus T1. For Cb and Cv, also from the table, 1.005 for Cb, and Cv is 0.718. With time, you will memorize these numbers. Okay. Okay. What about T3 and T2? I already found T3 and T2, so Qn is easy. For Qout, I have T1 in the question. Okay, it is given in the question, but T4, I can find it using this one. I have T3, I calculated in part A, and I have RC and R, I can find T4. Okay, so easy for the constant specific heat. We don't need a lot of interpolations, and usually in quizzes, inshallah, I predict that it is about constant specific heat, not variable specific heat. Even the midterm I'm fine, but I study everything. Okay. Sometimes variable specific heat came in the exam. Okay, so for part B, Wnet is equal to Qn minus Qout. I want to find Wn because I will use it again in the mean effective pressure. Okay, and then for thermal efficiency, it is Qn over what is Qn? It's equal to Wnet over Qn. Okay, so for Qn is equal to Cb T3 minus T2. Okay, Cb from the table is 1.005, T3 is 1818.86 minus 909.43. So Qn is equal to 913.98 kilojoule per kilogram. Okay, for Qout is equal to Cv T4 minus T1. Okay, Cv is 0.718, T4 is 791.7 minus 300 Kelvin. So Qout is equal to 353.04 kilojoule per kilogram. Then Wnet is equal to Qn minus Qout, and equal to Qn is 913.98 minus Qout 353. 0.04. So W net is equal to 560.94 kilojoule per kilogram. Okay. So for the thermal efficiency, W net over Qn, W net is 560.94 over Qn 913.98, and this will give you that the thermal efficiency is 0.6137, and it is predicted that it will be higher than the variable specific heat because it is not accurate like the variable specific heat assumption. Okay, so that is 61.37%. For T4, why need already calculate T4 or what? Yes, we calculated T4. Okay, we didn't calculate T4 yet. I was just copying from the paper because I talked about this T4. Okay, so T4, this one we calculate from here. T4 over T3 is equal to RC over R power K minus 1. Okay, so T4 is equal to T3 R3 over R power K minus 1. T3 we found it in the part A, so T3 was 1818.86, and RC is 2 over 16, K is 1.4 minus 1, so T4 is equal to 791.7 Kelvin. That is why where from that's from where this number came. Okay. خلاص. We found everything. The meaning is the mean effective pressure. The mean effective pressure is the same equation, W net over V1 minus times 1 minus 1 over R. V1 from the ideal gas law, V1 is equal to R T1 over P1. R is 0.287, okay, times 300 Kelvin over B1 95. It will be the same for V1, the same for constant and variable, it doesn't matter, 0.9063 meter cubed per kilogram, but the mean effective pressure will change because the W net already changed. Okay, so W net is 560.94 over 0.9063 times 1 minus 1 over 16. And this will give you that the mean effective pressure is 660.2 kilopascal. So it is much faster than the variable specific heat. And look like variable specific heat, all this, and for constant specific heat, half of the solution. Okay, the last question in this video, it will be a short question. We have an ideal diesel cycle has a compression ratio of 17, so R is equal to 17, and a cutoff ratio RC is equal to 1.3. Determine the maximum temperature of the air. Maximum temperature of the air. Okay, for diesel cycle, the maximum temperature, as you can see, is T3. So he wants to find T3. Okay, the maximum temperature. Okay. So we need to find T3 and the rate, and the word rate means dot, okay, power, kilowatt, kilojoule per second of heat addition to this cycle. Yani we want also to find the rate of heat addition. So the rate of heat addition is Q dot N. This one is in kilowatt, okay, and it's equal to kilojoule per second. Okay, we want to find Q dot N. To this cycle when it produces 140k of power. So power also means dot, rate, okay? So we have W dot net, okay? That is power, 140 kilowatt, okay? And the state of the air at the beginning of the compression, so at state 1 here, okay? We have a pressure P1 is equal to 90 kilopascal, and a temperature T1 is 57 degrees Celsius and equals 330 Kelvin. Okay, use constant specific heat heats at room temperature. Okay, we will use the constant specific heats. I want to find T3. Okay, like the same, the previous question, we want to find T3. I have RC, but I don't have T2. I can get T2 from here. I have T1 in the question, so that is the same procedure. Okay, so let's find it quickly. T2 over T1 is equal to R power K minus 1, and this will equal to T2 equal to T1 R power K minus 1. So T2 is equal to 330 times R 17 power 1.4 minus 1, and this will give you 1024.93 Kelvin. Okay, then RC is equal to T3 over T2. So T3 is equal to RC T2. RC is 1.3, T2 is 1024.93. So T3 is equal to, that is the first requirement, is 1332.41 Kelvin. Okay. For the thermal efficiency of diesel, for the Q dot N, okay, Q dot N for diesel here, I can see it here in this equation. Okay. What else I can find Q dot N. Okay, I have in the question also here W dot net. And I cannot see W dot net in the any of the equations, and it is given in the question. So I can predict that I will use this equation, and I want to find Q dot N. No need to find Q dot out. It will take time. I don't know if we can find it already. Okay, but I have W dot net. Okay, so that is an advantage. But to find Q dot N, I need thermal efficiency, and already usually we find thermal efficiency from W net over Qn, or W net over Qn capital, or W dot net over Q dot over Q dot N. Okay, but I don't have the thermal efficiency. I already need to find Q dot N, so I cannot use any of this equation for thermal efficiency. So that is why this question cannot be solved using variable specific heat, because we have an equation for the thermal efficiency of diesel in terms of the compression ratio and the cutoff ratio. Okay, I have the cutoff ratio and the compression ratio in the question is given. So if I find the thermal efficiency from here, it will equal to this one, and then I have W dot net given in the question. I can find Q dot N. Okay, and if you remember about the thermal efficiency of Otto cycle under the cold air standard assumption, or constant specific heat, this was the term for the Otto cycle. If we go to the Otto cycle, this was the thermal efficiency. It is the same term here, but it is here in the diesel cycle, but it is multiplied by another term in the bracket, this term. Okay, this term is always bigger than 1. We will not go for the derivation. I don't know actually the derivation of this one. I didn't try. Okay, but it is also always bigger than 1. Okay, so if it is bigger than 1, okay, this means that it will increase the term 1 r k minus 1. If we have 1 r k minus 1 and you multiply it by something higher than 1, it will increase its value. Then this term is already subtracted from 1. So if we increase this value, you will decrease the whole term, and then you will decrease the thermal efficiency. Okay, so we can talk about this thing using this graph. That for Otto cycle, we didn't talk about this for Otto cycle before, that the compression ratio, by increasing the compression ratio, you can see that the thermal efficiency of Otto is increasing. Okay, for example, at K equal to 1.3 at compression ratio, the efficiency was so low, less than 0.2. But here, by increasing the compression ratio to P12, the efficiency is around 0.5. So by increasing the compression ratio, if it will come in the exam, third question, what will happen for the Otto cycle and even diesel cycle by increasing the compression ratio? What will happen for the thermal efficiency? Okay, it will increase. Okay, and also for the specific heat ratio K, by increasing the specific heat ratio K from 1.3 to 1.4, 1.6667, also the thermal efficiency is increasing. For example, here for K equals 1.667 with around compression ratio of 12, the efficiency is around 0.2, 0.8. Okay, but here for also the same compression ratio with specific heat ratio less than 1.667, 1.4, we have a thermal efficiency of 0.6. So the thermal efficiency of the Otto cycle increases with the specific heat ratio K of the working fluid, which is air. Okay. For diesel cycle, the same, by increasing the compression ratio under a constant specific heat ratio K. The compression ratio, by increasing the compression ratio, will have a higher thermal efficiency. The comparison here, that the Otto cycle, okay, will stop here at the compression ratio of 12. But for diesel cycle, we can continue until we reach around 22, 23, 24. Okay. So that is the typical compression ratios for diesel engines. Okay. So by increasing the compression ratio, the thermal efficiency will increase. What else we can change? We make the constant specific heat ratio constant by increasing or decreasing the cutoff ratio. What will happen for the thermal efficiency under the same compression ratio? Okay, so if we have the compression ratio, for example, 12 for Otto and diesel cycle, okay, we will have, for example, if we have a cutoff ratio of 4, the thermal efficiency will be around less than 0.5. But if we decrease the compression ratio, the thermal efficiency will increase. So by decreasing the RC, the cutoff ratio, the thermal efficiency for diesel and Otto cycle will increase, because the thermal efficiency for Otto cycle, the cutoff ratio is 1. We didn't have cutoff ratio for Otto. Okay, so as you can see, for Otto, the minimum cutoff ratio is for Otto cycle. It is equal to 1. Okay. So for Otto cycle, at the same compression ratio, it will have higher efficiency than diesel cycle, because diesel cycle already will have a cutoff ratio. So it will be 2, 3, 4, 1.2, 1.3 here. Okay, for the same compression ratio, and this is important, not for different compression ratio, is for the same compression ratio, for the same R. Okay, the thermal efficiency for Otto is always higher than the thermal efficiency for diesel. Okay, but so what is the benefit of diesel? Why we are using diesel engines? That is the point, that for diesel engines we can increase the compression ratio more than 12. Okay, now for Otto cycle we have a compression ratio of 12. Okay, and cutoff ratio of course 1, so the thermal efficiency is around 0.65. okay, but for diesel engine or the diesel cycle, I can use a compression ratio higher, like for example 22 for example here. Okay, and with a cutoff ratio 1.2, 1.3. okay, it will be higher than the Otto cycle. So the diesel cycle can give me an efficiency higher than Otto cycle, because I can increase the compression ratio. Okay, you can read about this in the book. Okay, here about for the Otto cycle, and you can find it here also for the diesel cycle cutoff ratio. So that is for as you can see, thermal efficiency for Otto is higher than diesel on the same compression ratio if the both cycles operate and on the same compression ratio. Okay, so that is for this equation for the thermal efficiency of diesel. So returning back to our question, okay, we want to find the thermal efficiency. In order to find the thermal efficiency, we'll use this equation, because I already have R and RC, and then by using that, the thermal efficiency of diesel from this equation is also equal to this equation. It is also for diesel, okay, I can find Q dot N. So first, let's find the thermal efficiency for diesel using the new equation. 1 minus 1 R over K minus 1. This one is written like this. As you can see here, only the 1 over r power k minus 1 is multiplied by this bracket. Okay, do not put a bracket like this, okay, and multiply both of them, it will be a different number. Okay, only this bracket is multiplied by 1 over k minus 1. Okay, so let's substitute and be careful because big equation, and you may made a mistake. Okay, so we will have RC power k minus 1 over k multiplied by RC minus 1, and this will give you that the thermal efficiency is equal to 1 minus 1 over 17, 1.4 minus 1. Put the same bracket, يعني I'm using 1.3 power k, which is equal to 1.4 minus 1 over 1.4, 1.3 are cutoff ratio minus 1, and this will give you that the thermal efficiency for diesel is equal to 0.6597, and will give you that it's equal to 65.97%. So I can use this equation. Thermal efficiency is equal to W dot net over Q dot N. Okay, and I want to find Q dot N. So Q dot N is equal to W dot net over thermal efficiency for diesel. So W dot net is what? W dot net is 140 given in the question over 0.6597, and this will give you 212 kilowatt. Okay, so that is for this video. Inshallah, we'll have another video about diesel cycle, then we will go to the dual cycle.